Okay. So today, what we're gonna do is we're gonna go through and finish up 8.6, do anything 8.7. Remember, 8.6 was dealing with these power series. And a lot of what we did in 8.6 was seeing where these series converged and where they did not, where they diverged. And it all had to do with what was the fastest growth. In these power series, there's always an exponential piece around because we always have this x minus c to the nth power around. But inside the a sub n, there might be other either faster growth or slower growth. And so we saw a few of these last time and saw where the radius of convergence was. Okay. Whoops. So let's do another example of that, and then I will go into 8.7 and 8.8. Okay. We might do two examples. So let's look for the radius of convergence of x plus 3 to the nth power divided by n to the third. A little light. Change my marker. X plus 3 to the nth power over n to the third. Okay, so hopefully we see this x plus 3 to the nth power. That's exponential type growth. Into the third is into the p type growth. So this is going to dominate. It is the faster of the two growths around. If you had 3 growths or 4 different types of growth, you have to figure out which one is the fastest around. So the exponential is going to dominate. So this is going to act similarly to just summing up x plus 3 to the nth power from 1 to infinity. And I think about that as a geometric sum of a times r to the n. Here the a would be an implied coefficient of 1. The r would be x plus 3 to the n. I know that geometric series converges when r is between -1 and 1. Here, my r is the x plus 3 component. So my series converges when the x plus 3 is between -1 and 1. Subtracting 3 from all sides would say that my series converges when x is between -4 and -2. All right? That's what we call the interval of convergence. converge between -4 and -2. Okay. And my series diverges when x is less than -4 and when x is greater than -2. The last thing I would do is check the endpoints. By endpoints, I mean what happens at -4 and what happens at -2. So when x is equal to -4, I plug in -4 here, and I would get an infinite series that looked like -1 to the n over n to the third. That converges because of the alternating series test. In other words, my things inside there, 1 over n to the third is going to 0, it's decreasing towards 0. So the series converges when x is -4. When x is -2, what we would end up with when I plug in -2 for x is just a 1 to the nth power, which is always 1, right? If it's +1 to the nth power, 1 times itself is just going to be 1 over and over and over. And it turns out this also converges because it's a p-series with a power of 3. P of 3. And since that's bigger than 1, remember P of a higher than 1, it converges. P of 1 or less, it diverges. So that's the idea of these. If you remember, that's the idea of how intervals converge, how we get those interval of convergence, and the endpoints. We look for the type of growth that dominates. If we have more than one exponential, we put both exponential pieces in. When I talk about what it's similar to, and then I create one big R. But here we only had one exponential component. The other is an n to the p type component, or polynomial growth. So there, that's what we do. Okay? In example 7, x minus 4 to the n is exponential, 7 to the n is exponential, 5n squared is obviously not. So the x minus 4 to the n over 7 to the n, that's going to be dominating. And we make x minus 4 over 7 as our r. I won't go through that one. I think we've done enough of those. However, I do want to make a couple of interesting observations. Okay. The first observation is that if I think of these infinite series as infinite polynomials. Well, I can take the derivative of any polynomial. And the way I do that is I take the exponent of the x out front, multiply by the n, and then lower the exponent by 1. Right? Any polynomial, I can do that. And notice that this is an n to the first type growth. That's not going to change what type of growth dominates in here. The same thing is true if I integrate. If I integrate my function, I would add 1 to the exponent, divide by n plus 1 for each thing. And dividing by n plus 1, again, that's like an n to the first type growth. That n to the first type growth is not going to be exponential. So noting that either multiplying by n or dividing by n minus 1 doesn't change what things are going to dominate, it turns out if my function is a power series, then the derivative of that function and the integration of that function has the same interval of convergence. Now, it has the same interval of convergence, but multiplying by n or dividing by n minus 1 may change how the endpoints work. Like in the last one we did on the board, my endpoints both converged. Well, one of those may converge and one of those may diverge if we take a derivative or if we integrate or if we take enough derivatives. So it's an interesting thing that if I have a power series, the derivative of that power series and the integration of that power series basically have the same interval of convergence as the power series itself. Okay. So I'm not going to do that last example. I don't think that's necessary. And I don't ask questions about the interval of convergence of derivatives. So I don't think, it's an interesting observation. In this class, we don't use it a whole lot. I might make a point of it in the next section or the next 2 sections as more of an observational thing. But it's not something that we deal with. Like, it's not something that you're going to be asked questions on. So let's take a look then at the next section, which is Taylor polynomials. So the goal of a Taylor polynomial is to make an approximation of a function. And the way we're going to make an approximation is we're going to build a polynomial to make that approximation, because polynomials are fairly nice to deal with. And not only are we going to approximate the function, but we're also going to have to specify where we're approximating the function. So what we have to do is we have to choose a function and where we want to approximate that function. And we're gonna build a polynomial that's gonna look like that function around that point called the center. So we're gonna approximate it near a number, we call that number the center. And we're gonna build a polynomial which approximates the function pretty well around the center. The way we build that polynomial is that we make sure the derivatives are correct at C. And you might say, which derivatives? Well, all of them that the polynomial can take on. If the polynomial is a constant, then the first derivative becomes 0 and we don't deal with it. If the polynomial is linear, then we make the first derivative correct. If the polynomial is of second degree, we make the first derivative and the second derivative correct. This will make more sense when we get into an example. When I say making the first and second and third derivatives correct, what I mean by that is I want the function to match the polynomial at center C, but then I want the first derivative of the function to be the same as the first derivative of the polynomial at C, and the second derivative of the function to be the second derivative of the polynomial at C, and so on and so forth until I get to some n, which is going to be the degree of my polynomial. So whatever the degree of my polynomial is, I want that many derivatives to match up at C. Now, how are we going to force that? That's the big issue. And I'll kind of go through an example, and then I'll give you the definition of a Taylor polynomial and how to get that. So let's pretend we're dealing with the function f of x equals e to the x power at center of 0. So what I do is I say I want a cubic third degree polynomial to approximate the function near 0. So I want my third degree polynomial to approximate the function near 0. Since I know it's going to be third degree, I'm going to take derivatives of e to the x. Now, the nice thing about e to the x is that when I take a derivative, I get back e to the x. So actually, let me put this here too. I'm just gonna do that. So here are my derivatives. And what I need is I need a polynomial to match those derivatives when I'm near zero. So what I want to do is I want to figure out that when you plug in zero, e to the zero is a 1. Notice that in this case, that means every derivative, my first derivative, my second derivative, and my third derivative at zero should end up being 1. Now, I'm going to show you why we get what we get in just a moment. Well, let me restate this. I'll give you a nice short form in just a moment for how we're going to come up with the coefficients. But for right now, I want to show you why they are what they are, why they come up to what they are going to be. I want a third degree polynomial. And the way we usually denote that is a P with a sub 3 for third degree polynomial. And I wanted it centered at 0. Centered at 0 means that I'm going to have a constant, and then I'm going to have a first term with just an x. Just like when we're dealing with infinite series, when we say centered at a c, we're talking about x minus c to different powers. So that's the linear term. This will be the quadratic term. And this will be the cubic term. And I don't know those coefficients yet. But I want you to notice something about this polynomial. If you plugged in 0 into this polynomial, you would get a sub 0. Because this term, and this term would all be 0. So if I took a derivative of the polynomial, the constant goes away, I would take a derivative here, I'd get 1a1 plus 2a2 x to the first plus 3a3 x squared. Again, derivative, I'm just taking the exponent out front and then lowering the exponent by 1. Notice what happens when I plug in 0 into the first derivative. I simply get my coefficient a1. If I take a second derivative of my polynomial, that's just a derivative of this, I'm going to get 2a2 times 1 plus 3a3 times 2 times x to the first. So that's going to be a 6a3 times x to the first. Notice that when you plug in 0 into that polynomial, you don't get A2, but rather you get 2 times A2. Now let's check out a third derivative. A third derivative would just be a derivative of this. This becomes 0. This becomes 6A3. And notice that if you plug in 0, you get 6 times A3. Now, what did we just say? We want a polynomial of third degree centered at 0. This one is centered at 0. Such that this matches up with this. And this matches up with this. And this matches up with this. This matches up with this. In other words, all of the derivatives should match up with the function values, with the derivatives of the original function evaluated at 0. Okay? So in other words, we need f of 0 to be my polynomial at 0. That means, oh, there you go. 1 is equal to the constant number of my polynomial. We also need the first derivative to match up with the first derivative over here. That means 1 needs to be equal to A1. We also need the second derivative of the function to match up with the second derivative of the polynomial at 0. Second derivative of the function is 1. Second derivative of the polynomial is 2 times A2. That means the coefficient of my polynomial on the squared term needs to be 1/2. And lastly, we need the third derivatives to match up at the center. That means 1, third derivative over here is 1, needs to be equal to 6 times A3. That means the coefficient of my x to the third term needs to be 1/6. So I claim that the polynomial that approximates that we're trying to get here, the third degree polynomial that approximates, needs to be the following polynomial. 1 plus 1x plus 1/2 x squared plus 1/6 x to the third. I would have written this one over there, but I didn't want to move the board. So polynomial that approximates is this one. And let's see that graphically. So let's take a look at the graph of both of my function and my polynomial. Oops. So here's my polynomial. It's in, oh, sorry, 166 cubed. There we go. Here's my polynomial in blue. That's 1 plus 1x plus 1/2 x squared plus 1/6 x to the third. And here in red is my function. So what you see is, obviously these don't match up very well if we're out here at like -4. But if we're close to 0, where the center was, then my function and my polynomial are very, very close to each other. And they're exactly the same at that point. So this polynomial will approximate the function very well, close to x value of 0. So that's what we're doing. We're creating a polynomial that really matches the function well, close to whatever center value it has. Now you might say, what would happen if we were talking about an approximation for e to the x centered at a different number, centered at 2, for instance? I'm not going to go through all of this, but if we were centered at 2, obviously I'd be plugging in 2 everywhere. So I'd get different outputs. Again, you don't have to write this down. I'm just going to, because the next slide is what's important, not this one. So you're going to get different outputs. And instead of your polynomial looking like this, every time there's an x, it's going to be replaced with an x minus 2. And notice that when you take a derivative, well, let's start. Again, I'm not going to go through all this, but if I plugged in 2 to a polynomial that looked like this, where I have x minus 2 instead of just the x, notice if I plug in 2, all of these go to 0. So I get back a sub 0. And then if I take a derivative, this goes away. This just becomes a 1 plus 2a2 x minus 2 to the first plus 3a3 x minus 2 squared And then you plug in a 2 to that, and you get a 1. And then if you take a second derivative, you get 2a2 plus 6a3 times x minus 2 to the first. If I plug in a 2 for that, I get 2a2. If I take a third derivative, I get 6a3. And if I plug in a 2 for that, I get back 6a3. Notice that by using x minus 2, I get the same pattern, a naught, a1, a2, a3. To me, when I say a2, 2 times a2, 6 times a3, etc. So the right-hand side of each of these equations is going to be the same. The left-hand side, instead of being f of 0, would be f of 2, which would be e squared every time. Hopefully that makes sense. And so because we have the same pattern over and over, we can start making some observations. Like every time I look for the coefficient in my polynomial, what am I going to be doing when I get down to the coefficient a sub 3? Well, that coefficient is always going to be my third derivative plugged into my center. I should say my center plugged into my third derivative divided by 6. Every time I get to my second derivative, it's going to be my center plugged into my second derivative divided by 2. Every time I'm talking about a first derivative, every time I'm dealing with coefficient of x to the first, it's my center plugged into my first derivative divided by 1. By the way, we could continue this pattern on if we wanted a fourth degree. If we wanted a fourth degree, what's going to happen? Well, in the first derivative, well, plugging 2 in, gonna wipe it away. First derivative, it's gonna be 4 times a4 times x minus 2 to the third. When I take a derivative of that, I'm gonna have 4 times 3, which is 12, times a4, x minus 2 squared. When I take a derivative of that, I'm gonna have 2 times 12, that's 24, a4 times x minus 2 to the first. And if we wanted to do a fifth degree, we could do the same thing. Notice that if I did a fifth degree, five would come out front, a5. Then in the next derivative, I'd be multiplying by 4. Then in the next derivative, I'd be multiplying by 3. Then in the next derivative, I'd be multiplying by 2. So what I would have done is I'd multiplied by 5. then by 4, then by 3, then by 2, and then ultimately by 1. That's 5 factorial, right? 5 times 4 times 3 times 2 times 1. And if you think about what these coefficients are, this coefficient on my first derivative of a1 is a 1. This is a 2, and then a 6. That's 1 factorial, 2 factorial, 3 factorial. My next is going to be 4 factorial. Then I'm going to do 5 factorial, and et cetera, et cetera. So all of that is to say the following. We can shortcut finding this polynomial by saying, because of the way derivatives work, if we want to get a polynomial of degree n, which approximates a function close to a center, we're going to have a polynomial which is going to have a constant plus a linear term, which has x minus c in it, then a quadratic term, which has x minus c squared, then x minus c to the third, a cubic term, however many degrees we want. And then the coefficients are always going to be the nth derivative divided by n factorial. And that's going to be the coefficient in front of x minus c to the n power. This is what's called the Taylor polynomial, specifically the nth degree Taylor polynomial, centered at C. You might see the phrase Maclaurin polynomial. That's the Taylor polynomial when we have center of 0. Center of 0 is a fairly common center. So we have a different name for that, named after another person. So Taylor is the last name of a mathematician. Maclaurin also the last name of a mathematician. But the coefficient is the important thing. Coefficient is always the nth derivative evaluated at the center divided by n factorial. That's the coefficient for every x minus c to the nth power. So let's do an example. We're going to find the third degree Taylor polynomial for f of x equals 2 to the x power centered at 3. Now, what I like to do is I know I'm going to have to find derivatives, and I'm also going to have to know what those derivatives are when I plug in my center. So I start with that usually. Okay, I start with that usually. So that's what I'm going to start with here. I say f of x is 2 to the x power. Since we're centered at 3, I'm going to plug in 3. 2 to the third power is 8. Then I'm going to take a derivative. Now the derivative of 2 to the x is 2 to the x times natural log of 2. Because the base isn't e, we have to multiply by natural log of 2 every time we take a derivative. And if we plug in the center into the first derivative, we get 8 times the natural log of 2. Go and calculate the second derivative. If I take another derivative of this, I'm going to have to multiply times another natural log of 2. So I'm going to get natural log of 2 times another natural log of 2. So natural log of 2 is being squared. Just so we're all on the same page, 2 is not being squared. The natural log of 2 is being squared. Might as well take a third derivative before I plug things in too. Sometimes I take all the derivatives, then plug in 3 and everything. Other times I'll just start plug in 3 and then take a derivative and plug in 3 and take a derivative and plug in 3. It really doesn't matter which way you do that. If I take another derivative, I'm going to have to multiply it times another natural log of 2. So I'm going to multiply it times natural log of 2 3 times. Now, we already plugged in 8 to my original function. Or I apologize. We already plugged in 3 to my original function and got an 8. We plug in 3 to the first derivative and got 8 times natural log of 2. If I plug in 3 into the second derivative, I get 8 times the natural log of 2 squared. And if I plug in 3 to the third derivative, I get 8 times the natural log of 2 to the third power. Now, the third degree Taylor polynomial, I'm going to write an extra step that I usually don't, just for the sake of your notes. We're going to have a constant. We're going to have x minus 3 to the first power times a coefficient. We're going to have x minus 3 to the second power times a coefficient. And we're going to have x minus 3 to the third power times some coefficient. And what that previous slide said was that if we are centering at 3, this constant term is just going to be f of 3. This coefficient in front of the x minus 3 is going to be f prime evaluated at 3 divided by 1 factorial. By the way, 1 factorial is just 1, so you can just put f prime of 3 if you wanted to for that one. My degree of x minus 3 to the second power, my coefficient here, is going to be f second derivative evaluated at 3 divided by 2 factorial. And my coefficient of the x minus 3 to the third power, that coefficient is going to be f third derivative evaluated at 3 over 3 factorial. So that's what the Taylor polynomial centered at 3 of degree 3 is. So that's the third degree Taylor polynomial centered at 3. And what I have to do is I just have to, now that I know all of these, I just plug those in. It's going to be a little bit messy, but we get 8 plus 8 times natural log of 2 over 1 factorial. Times x minus 3. This is 8 times natural log of 2 squared over 2 factorial, which is 2, times x minus 3 squared. And then this is 8 times natural log of 2 to the third power divided by 6 times x minus 3 to the third. That's my third degree Taylor polynomial. Now, obviously, that's kind of an ugly looking polynomial because we have natural logs of 2s lurking about there. But this is going to be a polynomial which approximates this function really, really well, close to x values of 3. Okay. Let's look at another. This says, let's find the 5th degree Taylor polynomial centered for natural log of x centered at 1. So 5th degree Taylor polynomial for natural log of x centered at 1. And then I am going to see how well this approximates. Okay, so let's worry about the 5th degree Taylor polynomial, and then we'll do the approximation. So I'll talk about how well this approximates and that kind of stuff. All right, so let's do the following. Since it's 5th degree, I'm going to need to take 5 derivatives. So I'm just going to start taking derivatives. First derivative of natural log is 1 over x, or you can think of that as x to the minus 1 power. In fact, that's how I'm going to think of it when I take my derivative. And then when I plug in 1, I'll plug it into 1 over x. Hopefully that's not too much of a stretch. When I take my second derivative, -1 is going to come out front. I'm going to lower my exponent by 1. So that's -1 times x to the -2. If I write that as a fraction, that's -1 over x squared. If I take my third derivative, -2 times -1 becomes a 2. And then I lower the exponent by 1, so that -2 becomes a -3. And I get 2 over x to the third. My fourth derivative. Oftentimes, after you take a bunch of derivatives, you don't write all the slash marks. You just write, hey, this is the fourth derivative. So you just write a 4, like in an exponent with parentheses. -3 times 2 is -6. Lower your exponent by 1, you get a -4. As a fraction, that's -6 over x to the fourth. And then my fifth derivative, -4 times -6 is a positive 24. Lower my exponent by 1, I get x to the -5. Which as a fraction is 24 over x to the fifth. Now we wanted to center this thing at 1. So let's go ahead and plug in 1 into my function and all of its derivatives up till fifth derivative. I don't know if you've all seen that notation for fourth and fifth derivative yet, but that's what it is. A lot of times people just put in parentheses. Kind of looks like a power, but you're not taking it to a power, you're taking fifth derivative. All right, so if I plug in 1 here, natural log of 1 is 0. If I plug in 1 here, 1 divided by 1 is 1. If I plug in 1 into the second derivative, I get -1 over 1. So I get -1. If I plug in 1 into my third derivative, I get 2 over 1, which is a positive 2. If I plug into my fourth derivative, I get -6 over 1, which is -6. If I plug in 1 into my fifth derivative, I get 24 over 1, which is 24. I need all these for my fifth degree Taylor polynomial because my fifth degree Taylor polynomial, and I'm just going to write it out, is going to be my constant, which is going to be f of 1, plus first derivative evaluated at 1 divided by 1 factorial times x minus 1 to the first power, plus my second derivative evaluated at 1 over 2 factorial times x minus 1 to the second power. So the powers and the factorials always have to match up. And then the center, what you plug into your derivative, and your center are always going to match up. Third derivative, plug in 1 divided by 3 factorial times x minus 1 to the third power, plus fourth derivative, plug in 1 divided by 4 factorial times x minus 1 to the 4th power plus 5th derivative, plug in 1 over 5 factorial times x minus 1 to the 5th. Cool. That's a long one. A lot of writing, but it's 5th degree, so it's quite involved. Now let's plug in the numbers we just found. F of 1 is a 0, so this thing is 0. F prime at 1 is 1. Second derivative at 1 is a negative 1. Third derivative at 1 is a 2. By the way, 3 factorial is 6. I didn't say that. 2 factorial is 2. Fourth derivative. When I plug in 1, I get a negative 6 over 4 factorial, which is 24, times x minus 1 to the 4th. Fifth derivative at 1 is 24 over 5 factorial, which is 120, times x minus 1 to the 5th power. So that's my 5th degree Taylor polynomial for natural log of x centered at 1. I am going to rewrite that and just simplify each one of these coefficients. In this case, I get 1 times x minus 1. Then I get a minus 1/2 times x minus 1 squared. Simplifying 2/6 gives me a positive 1/3. I'm going to multiply that times x minus 1 to the 3rd. Simplifying 6 over 24, negative 6 over 24, I get a minus 1/4 times x minus 1 to the 4th. And 24 over 120 becomes a positive 1/5. And I'm going to multiply that times x minus 1 to the 5th power. Okay. So that's the 5th degree Taylor polynomial that mimics natural log of x close to a value of 1. Now, I want you to see how this is actually going to look graphically. Oh, did I screw that up? Plus 1/3 x minus 1 to the 3rd power. Excuse me. Notice that this is a polynomial which really mimics natural log of x close to the value of 1. When we're close to the value of 1, we really mimic this well. Okay. And so if I were trying to approximate at 1.05, for instance, actually, let's just let my if I said, what is f at 1.05? You just plug in 1.05 into natural log, and you get 0.048790, blah, blah, blah. If I said, what's my polynomial at 1.05? I plug in 1.05 into my polynomial. Notice that up till 1, 2, 3, 4, 5, 6, 7, 8, basically 8 decimal places, they're the exact same thing. So this mimics the function really well close to 1. It looks like the same thing up to 8 decimal places. Now, let's talk briefly about what if somebody said they actually wanted to find the 3rd degree Taylor polynomial, centered at 1 for natural log of x. Well, if you wanted to find the 3rd degree Taylor polynomial, with center 1, all of this would have been the same. The first 3 derivatives I would have had to figure out. Then I would have plugged in 1. And then I would have only gone out to this much. And so the 3rd degree Taylor polynomial would essentially be the exact same thing as my 5th degree, but with the 4th and 5th power terms lopped off. Okay. So with the 4th and 5th power pieces lopped off, you get the 3rd degree. And you can imagine if you wanted the 6th degree, you just have to add on a 6th term. And if you wanted the 7th degree, you'd have to add on a 6th term and a 7th term. Now I want you to notice something about the 3rd degree. Because it has less terms, let's take another, I'll use A. I don't know. Instead of, because it has less terms, I didn't write sub 5. It's gonna match up pretty well still at 1. But remember, we're trying to approximate this red. It's gonna be further away from this red quicker. Uh-oh, I screwed that up. Sorry. Let's do A. Good. Ah, I keep hitting the wrong thing. Trying to hit that. Okay. And let's say we wanted to approximate using a 3rd degree Taylor polynomial instead of a 5th degree. It's still going to be a pretty darn good approximation at 1.05. Let's zoom in to 1.05. Still going to be a pretty good approximation, but hopefully you notice that it differs in the 6th decimal place from what the actual function value is. Whereas our original differed in the 9th decimal place. So you get a better approximation with a 5th degree than you do with a 3rd degree. That's the point of that. So when you're doing approximations, a 5th degree Taylor polynomial is going to approximate better than a 3rd degree Taylor polynomial. And so on and so forth. I don't know what that is. Huh. Weird slide things. Now, we're going to return to this in just a moment, this 5th degree Taylor polynomial. But what I would like you to do is try to find the 4th degree Maclaurin polynomial. Remember, Maclaurin just means center is at 0 for cosine of x. So cosine of x centered at 0, 4th degree. All right, so let me go through this. Hopefully you got at least a little bit of it. So we're talking about cosine of x. If I take the derivative of cosine, I get negative sine. If I take the derivative of negative sine, I get negative cosine. If I take the derivative of negative cosine, I get positive sine. And if I take the derivative of sine, I get positive cosine. So we jump back and forth between negative, positive, cosines, and sines. I'm centering this at 0, and I know that because it's called the Maclaurin polynomial. So I plug in 0 into my function. And if you want, you can type into your calculator cosine of 0, or just by knowing how cosines and sines work, cosine of 0 is 1. Sine of 0 is actually 0. So negative 0 is 0. If cosine of 0 is 1, then negative cosine of 0 is negative 1. And if, well, sine of 0 is 0, cosine of 0 we're back to a positive 1. So my fourth degree, I don't want to do this in blue because we got some blue on the board. So my fourth degree Taylor polynomial, or in other words, my fourth degree Maclaurin polynomial in this case, is going to be f of 0 plus f prime of 0 over 1 factorial times x minus 0 to the first. I'm just going to put x. Second derivative at 0 over 2 factorial times x minus 0 to the second power plus third derivative at 0 over 3 factorial times x minus 0 to the third power plus fourth derivative at 0 over 4 factorial times x minus 0 to the fourth power. F of 0 is 1. Then I get 0 over 1 factorial times x plus negative 1 over 2 factorial times x squared plus 0 over 3 factorial times x to the third plus 1 over 4 factorial x to the fourth. Notice what that fourth degree polynomial is. That fourth degree polynomial is going to be 1 minus 1/2 x squared plus 1/24 x to the fourth. And that's a pretty easy polynomial to deal with. Pretty easy polynomial to deal with and approximate with. In fact, if we do want to approximate, well, I like to use my calculator or Desmos to approximate efficiently. So let's go ahead and do that. Let's take f of x equals cosine of x. And then I'll use my polynomial that I just had, 1 minus 1/2 x squared plus 1/24 x to the 4th. Notice that that polynomial works really, really well around when my x is 0. But as I get further and further away, obviously, way out here when x is 4, it's going to be a terrible approximation. If you plug in, for instance, 0.5 into your polynomial and into your function, notice how close they are. They're the same for 3 decimal places, and they differ at the 4th decimal place. If I plug in 0.02, well, 0.02 is going to be closer to my center than 0.5 is. So notice that if I plug in 0.02, that's very close to my center. And on Desmos, that gives me the exact same rounded value up to 12 decimal places. And so what I'm saying is that you get good approximations close to your center. And the closer you are to the center, the better approximation. The higher degree polynomial you get, the better approximation as well. And that's really what 8-7 is all about. Maclaurin and Taylor polynomials give you good approximations around the center. The closer you are to the center, the better approximation you get. And higher degree polynomials give you better approximations as well. There is a formula that tells you how much of a difference there can be between the original function and Taylor polynomials. I don't need you to know this formula. All I want you to know is the 2 things I've said. You get better approximations when you're closer to the center. The further you are away from the center, the worse the approximations get. And the higher degree polynomials give you better approximations as well. Now, the last section that we're going to cover is on Taylor series. So we just did Taylor polynomials, and now we're going to do Taylor series. So the big idea is that we want to turn our function like cosine or like natural log into an infinite series. Now, one way we can do that is by the use of geometric series. And I'll show you how to do that maybe, well, actually, I'll probably show you in a video how to do that. But the other way is to use Taylor polynomials. Okay? Now, I'm going to talk really briefly about geometric series, but I'm gonna actually provide a video about this to you so you can study it tonight or something. Basically, the goal is to replace R in A over 1 minus R with an expression concerning X. So if I have a function that looks like 1 over 9 minus X, I can change that into something that looks like A over 1 minus R with some algebraic techniques, and then just make sure that we rewrite it as in geometric power series. Okay? The trouble with that method is that not all functions can be written as A over 1 minus R. Things like e to the x, things like sine x, you can't really easily write as A over 1 minus R. So we need a new technique. And the reason that 8.8 doesn't take too long in terms of the Taylor series is that the main work has already been done. We've already dealt with Taylor polynomials. All we have to do to make an infinite series is let my Taylor polynomial go to n and let n approach infinity. So it's a Taylor series is basically an infinite Taylor polynomial. So what's the definition of a Taylor series? It's this. It's an infinite polynomial where each of the terms is coming from the Taylor polynomial. It's an infinite series where each term in the underlying sequence comes from a Taylor polynomial. And by the way, we call this Taylor series. It's called a Maclaurin series if we're centered at 0 still. Just like Maclaurin polynomials were centered at 0. A Maclaurin series is a Taylor series centered at 0. I'm looking for a good one. I'm going to skip around here a little bit. I hope that doesn't throw you off. Sorry. So let's use our work that we just did to try to figure out a Maclaurin series for cosine of x. Well, conveniently, we just did this. We just found a Taylor polynomial centered at 0, which is also Maclaurin polynomial. And we got this pattern. What is the coefficient? What are the coefficients here? Well, you'll notice that if I wanted to find an infinite series, I'm just getting the even powers of x. So I'm going to put this as 2n. Hopefully that's not going to throw you off. And we're going to start our count at 0 so we get the constant term. Notice that they alternate between positive and negatives on top, between +1 and -1. It's like 1/1 or whatever. So if they alternate, we're going to have -1 to the nth power. What's the denominators? Well, this denominator came from 2 factorial. This denominator came from 4 factorial. You can imagine the next denominator is going to come from 6 factorial. And the next denominator comes from 8 factorial, because every other one is 0. Does that make sense? Hopefully that makes sense. So cosine of x can be written as this infinite series on this infinite series interval of convergence. So once we've found a pattern, the Taylor series is just that pattern summed up to infinity. Let me give you another example. Previously, we found a Taylor polynomial for natural log of x with center of 1. If I said, let's find the Taylor series for natural log of x with center of 1, what I would do is I would look and just look for the pattern. Look for the pattern and try to write it down in infinite series form. What are these coefficients doing? This is 1/1, 1/2, 1/3, 1/4. Well, it's always going to be something over n times x minus 1 to the nth power. And we're alternating back and forth between positive and negative. We know how to do that. It's either going to be a -1 to the n plus 1 or a -1 to the nth power, depending on whether I get the positive first or the negative first. Here I get the positive in the odd exponents. So I need n plus 1 for my exponent. In the previous one, we needed -1 to the n. And because I don't have a 0 term, I'll start my count at 1. In other words, because I don't have a excuse me, constant term, a degree 0 term, constant term, I'll start my count at 1. And that's it. That's the Taylor series for natural log of n with center of 1. Okay. So we're simply coming up with the pattern that we saw earlier. Now, let me do this one. Let's come up with the Maclaurin series. For e to the x. That means centered at 0, right? We've actually done this one, at least some of this one. F of x is equal to e to the x. If you start taking derivatives, you just get e to the x back over and over and over again. Now you might ask, well, how many of these do we actually need? How often should I go? How far? How many derivatives should I take? And it kind of depends on you. If you're really comfortable seeing patterns and seeing how things are going to turn out, just taking a few derivatives will probably work. If you're not as comfortable, you might have to take more. Notice that all of these derivatives, when I plug in 0, give me the number 1. That means my polynomial is going to be, well, 1 plus 1 over 1 factorial x minus 0 to the first power. I can leave off parentheses there. Plus 1 over 2 factorial x minus 0 to the second power. Plus 1 over 3 factorial x minus 0 to the third power. Plus 1 over 4 factorial x minus 0 to the fourth power. And I can already see the pattern and how that's going to come up. My infinite series for e to the x, since I have a constant, I'll start my count at n equals 0. It's always going to be 1 over n factorial times x to the nth power. And what we're saying is that that infinite series doesn't just approximate e to the x. That's exactly equal to e to the x on the interval of convergence of this series. And here's a really interesting thing. If you go back to our last class period, we dealt with things like this. The n factorial is going to dominate. It's in the denominator. So the interval of convergence of this is everywhere. Is on all real numbers. So these are the same on the interval of convergence of the series. This series has interval of convergence of the entire number line, all real numbers. The other one I did, the one on the right-hand side of the board, this is equal to natural log of x on the interval of convergence. But the interval of convergence of this one is actually between 0 and 2. So it has a smaller interval of convergence. Doesn't it? The e to the x converged everywhere. This series converges only from 0 to 2 and not including 0. So that's basically what Taylor series is. I create a Taylor polynomial as far out as it needs to be. And then I say, well, if I let that go out to infinity, what infinite series would I get? And I'd have to rewrite that as an infinite series, this Taylor polynomial as an infinite series. Okay. All right, so for today, that's all we're going to cover on Taylor series.